Some of you know me, many of you do not. For 40 years, I was designer for the automotive industry. I've been retired for 14 years. I make and repair furniture. And as Linda and other research librarians will tell you, I do a bit of esoteric reading. One of the things you learn as a designer is that all design is synthesis. You approach a problem by creatively synthesizing ideas, elements, explanations really, in some new way to arrive at a solution. What I propose to do here is to synthesize a number of explanations for our electrical energy quandary, and I will provide attribution for my sources right before the break. In other words, I have taken sentences, paragraphs, whole tracts from others, and I make claim to authorship only for the synthesis. My plan is to lecture for 45 or 50 minutes, and then show a 5-minute synopsis of the Thorium video, and take a 10-minute break. Now this Thorium video, the library owns, and after this talk, it will be available to take out. It's 143 minutes long. I'm not going to show the whole thing tonight. After the break, maybe 40 minutes, and then maybe some discussion. Just a little thought as an aside, just to start with. The philosopher was named Gotthold Lessing. The aspiration to truth is more precious than its assured possession. There's something to chew on. Every human activity produces heat. One of the most useful and universal uses of heat is the generation of electricity. Your prosperity is a function of the electricity you use or is produced on your behalf. Worldwide, in the 82 nations with populations over 10 million, the threshold for prosperity is 2,000 kilowatts per year. Here in Charlevoix, for comparison, the average private usage is about 5,000 kilowatts per year. Now, the vast majority of electricity produced for human betterment comes from burning carbon, which is having an increasingly negative impact on our environment. Stephen Chu, probably one of the foremost scientists in the world. He was a Nobel laureate in physics, former director of Lawrence Berkeley National Laboratory, and now U.S. Secretary of Energy. Quote, "Overwhelming scientific evidence shows that carbon dioxide and other greenhouse gas emissions have caused our planet to change, and the effects are dramatically accelerating," unquote. Just consider our latest winter, the warmest on record. Oh, but you say, we've had warm winters before. Sure, but we've been contributing to global warming for over a century, and we're just starting to recognize it. I would add that in about 2 weeks, on 8th of May, there's a fellow named Peter St. Clair who's going to present right here on global warming. So I'm not going to say anything more else about global warming because I've looked at his blog and he's a master at it. I'll go on. The world population is now at 7 billion. And with a vastly increased need for electricity worldwide, we need to rethink our dependence on carbon to produce it. And I believe a relook at nuclear energy powered by thorium will provide the better alternative. Now I'm going to talk about this reactor, and then I'll talk about why we want to get away from carbon. The world-changing liquid-fueled thorium reactor, or lifter, will replace every other source of electricity in terms of cost effectiveness. Comparative advantages over solid-fueled uranium reactors include reduced capital cost, vastly reduced fuel costs, enhanced nuclear safety, minimum generation of nuclear waste, economical desalination of seawater, production of valuable medical and other isotopes, and further reduction of the risk of weapons proliferation. In fact, lifters, that's what I'll call them from now on. It's a liquid fuel thorium reactor. Lifters can burn the fuel from dismantled bombs and most of the waste from uranium pressurized water reactors, which is what the world uses today. Thorium reactors will be cheap. Building a 1 gigawatt thorium reactor or power plant will cost about $250 million or less because meltdown concerns can be tossed out the window. A thorium reactor does not, in fact, need a containment wall. It fundamentally changes the economics of nuclear power. Fuel costs. Today, the nuclear industry makes money primarily by selling fuel to reactor operators. As mined, uranium is only 0.7% pure. It has to be enriched to 3.7% to make it usable. And it costs $1,633 a kilogram. That's today. There's 4 times as much thorium in the Earth's crust as there is uranium. And in the US today, just in the slag piles from rare earth mining in America, there is a 400-year supply. Thorium comes out of the earth as pure, 100% usable isotope, and only needs to be refined to separate it from the monazite sands it occurs in. Once a refining facility is built, thorium will cost in the order of $10 a kilogram. That's a 500 to 1 advantage over uranium. Let's compare the daily fuel requirements for a 1 gigawatt plant using coal versus thorium. A coal plant requires 9,000 tons a day. That's 100 90-ton railroad cars. A comparable lifter uses 3 kilograms, that's about 6.5 pounds, of thorium, an amount you can easily hold in your hand were it not radioactive. Safety. A uranium reactor is an atomic pressure cooker. It will naturally overheat unless it's held back by a robust cooling system. Because of the constant danger of high pressure ruptures and steam leaks, it needs to be inside a containment vessel. A lifter is completely different. It is essentially a kettle of radioactive lava that never boils. This lava is super hot, but not under pressure. In a lifter, turn the page to 7. In a lifter, thorium is dissolved in molten liquefied fluoride salt. If it ever leaks out, actually it flows and looks just like green dish soap. There's no explosion because it doesn't use water to keep cool. A lifter heats a common gas like CO2 to spin a turbine. Since the liquid fuel is never under pressure, a leak would simply pool and cool, just like lava, quickly forming a blob of rock on the reactor room floor. Only 2% of the salt mixture is the actual reactive fuel, and every atom of thorium is chemically bonded to the salt. There are no radioactive particles floating around inside a lifter. Solid fluoride salt melts at 450 degrees C. With a full load of thorium, the temperature rises to about 700 C. That's about 1,300 degrees Fahrenheit. For comparison, inside an automotive engine, about 450 in the combustion process. If the liquid fuel starts to overheat, it expands, which separates the radioactive particles and slows the fission process, cooling the molten salt down again. Liquid fuel solves a critical problem of environmental safety. The other principal safety feature of thorium fuel is that it won't run without a starter or priming. Thorium needs a neutron source for the fission process to sustain, and there are a number of ways to do this. A lifter is a lot more like high-temperature plumbing than nuclear physics. Because molten salt sheds heat quite easily, an elaborate cooling system isn't needed. Since a lifter doesn't operate under pressure, high-strength valves, fittings, and pipes aren't needed either. Off-the-shelf parts will do. Backup generators, emergency cooling systems, control rod mechanisms, spent fuel storage pools, the crane for replacing fuel rods, reactor pressure vessel, that's the big cost, and the airtight containment dome. Those are all eliminated. Nuclear waste. No reactor is waste-free, but a lifter's waste will be minuscule. In a lifter big enough to power a city of 1 million, the yearly long-term waste would be 340 pounds, about the size of a basketball, and be virtually harmless in 300 years. The rest of the waste, 1,660 pounds, is short-term and is safe in 1 year. It would all fit under a card table, all of it. A secondary benefit of recirculating the molten salts, and that's a blend of lithium fluoride, beryllium fluoride, and thorium fluoride, is that valuable medical isotopes, such as bismuth-213, a smart bomb against dispersed cancers, you only need 1/1000th of a gram. In this video, if you're really interested, they explain it way at the end with a lot of graphics. Plutonium-238, which is another byproduct, NASA uses it to power batteries and deep space probes, and we don't have another way of making it, so it'd be a natural. Xenon and molybdenum also can be removed. All these byproducts that I've just named are valued at $250,000 a year. That's in addition to what you'd earn producing electricity. Lifters don't produce anything to make weapons from. They are proliferation resistant. Finally, lifters will be small and standardized, allowing them to be mass-produced in factories and shipped by rail. Their low-pressure components will be designed to be replaced when necessary and will be much easier to assemble, allowing for faster and simplified inspection. Lifters will be modular, so a power plant will be able to grow along with the city it serves. Now here's something that really be surprising to you. The footprint of a lifter is 2,000 to 3,000 square feet. That's about half the size of a standard city lot. And since they're so much safer, they can be close enough to become familiar, which will help to overcome our fear. One of the things that causes us to be fearful of something is if it's out of sight. If you're around it all the time, you get used to it, and your fear goes away. And also close enough to eliminate power line losses, which waste 10% minimum. All these factors and more will combine to produce a trickle-down efficiency, greatly reducing the complexity, cost, size, and build time of each project. More importantly, Thorium lifters will help wean us from a carbon economy. Before I switch the side, I want to tell you about the two guys in the picture. The guy on the left is Eugene Wigner, and I'll mention him later. He's kind of a scientist's scientist. He's probably up in the same strata with Einstein and Leo Szilard and, well, a bunch of other guys. The fellow on the right is Alvin Weinberg. And Weinberg was a student of Wigner's. And so I will describe these two fellows a little later on.